Okay, welcome back to Feedback Control Systems. This is Module 12.2, Stability, Gain Margin, and Phase Margin via Bode plots. The objectives of today's module are to look at range of gain for stability using Bode plots. Then we'll look at gain and phase margin for Bode plots. We previously saw that for the Nyquist diagrams that we saw in a previous lecture. Then we're going to relate closed-loop transient and frequency response. And then finally, we're going to relate closed and open-loop frequency response. So first, we'll start with our range of gain for stability using Bode plots. Have an example here, a G of S system. And what I want you to do is, here's three poles, a pole at 2, 4, and 5. And we're going to have a gain, so I want you to adjust the value of K to determine stability of the system. From our Nyquist slides from previous module, we have our three open loop poles here, and they are all in the left half plane. So in terms of stability, what we need for a closed loop stable system is we need the gain less than 1 relative to a when the phase is 180 degrees. So that's kind of our approach that we're going to apply relative to our Bode plots. So first of all, what we're going to do is we're going to set our gain K equal to 40 in order to get 0 dB at S equals 0. So where did this gain of K equal 40 come from? Well, I have with S equals 0, that S, and that S all go to 0, and I'm left with 5 times 4, which is 20, then times 2, which is 40. So if I have unity gain, log of that unity gain will result in 0 dB. So that's where I'm starting for a value of K. And then what each pole does, it will add minus 20 dB per decade slope. We saw that when we draw the Bode plots in terms of the asymptotes for each pole. Okay, so first, with the first pole is minus 2. And so what you'll see here at minus 2 is that first pole. So we go from 0, and then we're going to transition to the first minus 20 dB per decade. The second pole is at 4. So 1, 2, 3, 4 is right around there. So there, we're going to go add another 20 dB, so that'll go down at minus 40 dB. And then finally at 5, which is the next door neighbor, right there. At that point, now we have 3 poles. Now that slope is going to go down at minus 60 dB, and you can see that relative to the graphs as we're showing here. We can also look at the phase down below, where, again, once we start at the pole of 2, we'll go 1 decade below. So at 0.2, right here, it'll go down starting at minus 45 dB per decade. And then, again, 1/10 of 4, or at 0.4, you'll add another 45, and then so on. And then what you'll do eventually is you'll go starting at 10 times 2, which is 20. You'll start to re-add that 45 back in. So again, we should be able to draw the Bode plots based on these 3 simple poles. Then looking down below, looking at the magnitude plot, we'll see that there's a gain of minus 20 dB, certainly less than unity here. So relative to the gain less than 1 here, that actually is good. So the magnitude plot shows a gain of minus 20 dB when the phase is at minus 180. So here's minus 180 on the phase plot. So there's our intersection right there. And if we go up onto our Bode plot, what we'll see there is that we are well below, the unity here. And so now what we're going to do is we'll see that that's at roughly 7 dB. So here is the actual plot. Okay, and then you'll see that that's at, minus 20 dB at that frequency of 7 radians per second. So since we originally had a gain K of 40 and we are 20 dB below that point, what we can do is say, well, we could add another 20 dB to get that point to 0, and that's sort of the limit of stability. So adding plus 20 dB is a gain of 10, so 40 times 10 would result in a K of 400. So the system would be stable as long as we keep that gain K less than 400. Okay, so again, to summarize for this, we can vary K. We're looking at this plot. We initially set it with an initial K of 40 just to get a 0 dB. Then what we do is we look, where does this phase cross minus 180 go up? Find that frequency on the plot, see what sort of delta we have relative to that 0. In this case, it was minus 20 dB. So we can basically add another 20 dB on top of that, which again is a factor of 10. So 40 times 10 is 400. So as long as we keep that gain K less than the 400, we'll be a stable system. So in terms of gain and phase margin, what we essentially just looked at calculating was gain margin. So if we look at the phase plot, where the phase plot crosses 180, we go up from the phase plot to the magnitude plot, and what we'll see is like, well, how many dB are we from the 0 dB line? So that's that gain margin. For the previous plot with K equals 40, that was minus 20 dB of gain margin. So that's gain margin, but now we'll introduce phase margin here. And so for phase margin, what that is let's look at the magnitude plot where that crosses 0 dB, and then look down below, how much phase do we have until we hit 180? That's going to be referred to as the phase margin. So here is the Bode plots from the previous slide, again with K equals 40, because we start at 0 dB as shown there. So that's basically a repeat from the last slide. Now let's say we needed K less than 4,000 for stability. Let's just say we have a gain of 5x of so a gain of 200. So that would shift the Bode plot up by 5x, or a total of just under 14 dB. So again, this plot right here, this plot is for a K of 40, but I'm saying, hey, for a gain of 200, this plot we could just imagine shifting up by almost 14 dB. So at that case, so on this plot, again, what we saw for 7 radians per second, the phase margin, the gain margin was at minus 20 dB. So if we add that roughly 14, we're going to get a gain margin of roughly 6 dB when K is at 200. Okay, and then in terms of phase margin, what we'll see is when we have a gain of 200, the phase margin is found. We look again at the Bode plot relative to the 0 dB point, which again from the plot above will be shifted up by that 13.98 dB. So where does this equal essentially minus 13.98 dB as of right now? And that will be roughly 5.5 radians per second as shown there. And then so at minus 5.5 radians per second, the phase is at about 165, minus 165, right about there. And then so what we would have to do is subtract that from the 180, and we're going to get about 15 degrees of phase margin. Now what we want to do is relate the closed-loop transient and frequency responses together. Here is a unity feedback gain system here from our closed-loop transfer function. It actually looks like our general closed-loop second-order transfer function that we had studied a lot during modules in modules 4 range, and we looked at damping and natural frequency, the type of response, etc. So here's that open-loop transfer function G of S, and then the closed-loop function T of S. Now we can plot the magnitude of that response by substituting in S J omega. So by making that substitution, doing some complex math, we're going to get some magnitude function as shown right there. And then we could plot that magnitude in terms of decibels as a function of log frequency radians per second. Now, if we were to take this plot right here, and if our goal is to find that peak there, anytime we want to find a peak, we could utilize calculus, and we could take the derivative of this function, set it equal to 0, and that's going to find a local maximum or minimum. And so when we do that, what we can do is find this peak value MP, and what we'll do is we'll actually see that that's going to be essentially a function of the damping ratio as shown there. And then the frequency at which that occurs, that peak frequency, can be found as well. And so that might be useful to see as we draw that frequency response, that peaking, like how much is that peaking? And what we see is that peaking is related to the damping ratio, okay? And also that peak frequency as well relative to this term here, which we're going to see in a second, the bandwidth. Notice that the bandwidth is at minus 3 dB. Okay, so that bandwidth is related to the peak essentially by the natural frequency and also the damping ratio. So this last plot that I want to show on this slide is that there is this relationship, which is basically this plot of MP versus percent overshoot. Now here we're showing MP as a function of the damping, but in previous modules we also related that percent overshoot to that damping factor as well. So that kind of ties those all together, and then that kind of gives us a look into that closed loop transient response related to the frequency response as well. Okay, so we have that sort of tie back together. And continuing on this, this is the same plot we saw from the previous slide, that peak frequency and that peak magnitude there. The other term that we had here was the bandwidth, which again occurs at the minus 3 dB point. And so we could actually solve for that bandwidth as a function of just the natural frequency and just the damping ratio. So from our general second order transfer function, those are the two key things, the natural frequency, damping. And so again, now we have a mechanism to find this peak frequency, also the bandwidth as well. By these equations. And then once we have those equations, we know that there's a relationship relative to things like settling time and others. So that's what I'm going to show here, is this relationship between the natural frequency, settling time, and damping ratio. And so we can, first of all, find this bandwidth. So if we were to find the bandwidth here, then we could go in and actually substitute and find the settling time, again, as a function of the damping ratio. And here is a graph of that right there. So x-axis is damping ratio, y-axis is the bandwidth frequency times the settling time. So again, if we found the bandwidth here, sort of step 1, we could now find essentially the settling time here in step 2, because we already know the damping ratio. We needed that here to calculate the bandwidth. Next, we could rewrite our equation in terms of the peak time that we would have, where you'd get the peak overshoot in your time domain response. So here's again the peak time. We've already know the natural frequency and the damping ratio here. So again, now we have a plot that shows the bandwidth times the peak time on the y-axis and the damping ratio on the x-axis here. And then finally, there was a relationship to find the rise time. Really, it was the natural frequency times rise time from modules in the roughly the 4.2, 4.3 range, if I remember. And so again, we can also quantify that in terms of the rise time times the bandwidth as a function of the damping ratio, as shown here. So what we're showing is that even though we're looking here in these modules at the frequency response, there's a relationship how we can get those back into the time domain based on the natural frequency and damping ratio. Once we know those, we can then go back and find the settling time, peak time, and rise time as well to help characterize our time domain response. Further relating the closed loop and open loop frequency response, assuming we have a unity feedback system with our closed loop transfer function shown as there, we could then do our substitution of S equals j omega here. And then I'm showing something kind of new here, where what I'm doing is I'm going to take our transfer function g and substitute it into a real and an imaginary part. The real part being p, the imaginary part being q. Okay? So once I do that, as shown here, highlighted in green, I'm just taking that and translating that into a real and an imaginary part. And then with a little bit of manipulation, what I'm going to do is find the magnitude of the closed loop transfer function squared. So I'm actually taking the magnitude of this function here and then square it, and I'm going to get this relationship. And when I do that, I can rewrite this expression as shown down here, which if we go back to some algebra, we actually see that this is the equation of a circle. Okay, so with that, what we'll see is we're able to plot these, what we're going to call constant M circles over here. Notice the axes here, we're in the complex plane here, real and imaginary. And so this is essentially what we're going to do to look at some relationship, again, between the closed and open loop frequency response. So that's a starting point. And that's basically, these M circles are going to be essentially the magnitude, where, again, if we look on sort of the right of this line here, this line you can see is M equals 1. All the stuff to the right of that have smaller values of M, decimal values, 0.4, 0.5, 0.6, 0.7, etc. And everything to the left of that will be higher values of M, 1.3 here, again, trending down to 2. So those are all magnitude plots based on this closed loop transfer function here. So writing those as circles. So we can also do the exact same thing here for looking at the phase. And remember, the phase relationship is we take the imaginary part, which is Q, divided by the real part here, which is P. Now notice, because we have both a numerator and a denominator here. First, this is the numerator term, the inverse tangent of the imaginary over real. And then what I do is take here's the frequency response that I'm looking at here. So I first have the numerator, which is imaginary over real, this term, and then minus the denominator part here. So minus the denominator part where I have the imaginary part over the real part here, P plus 1. So that is how we would find the phase. And again, we can rearrange this, move the tangent over, and find the phase here. There is a trig identity, which I'll leave to you to go find, that essentially can relate this all together. And once we do this manipulation, again, we can make some definitions and rewrite this in terms of a circle. Now, don't worry about like some of the math and the derivation. We're never going to have you do derivations on a homework or an exam or stuff like this. But just wanted to show you, instead of just flashing up these circles and saying, hey, here's magnitude, here's phase, just wanted to walk you through at a high level of how we got there. So as long as you get that understanding of sort of directionally how we are getting to these circles, and you have a gut feel of where they're coming from, that's all I care about at this point. Okay, so you can look at this, and then what I have are what we're going to call these constant n circles, where these are a function of phase. And you can see a variety of phases here, plus 20, minus 20, plus 50, minus 50, etc. So these also on the real imaginary axis here, I have these sort of n circles that go this way that talk about phase, and these m circles that go this way that talk about essentially the magnitude. So a different way of looking at this, and we'll see going forward how we can use this. So with those M and N circle plots, they really can't handle changes in the gain. So as we saw with the Bode plot, as we changed the gain, we could look at moving that plot up and down and what that would do with gain and phase margin, etc. But with these M and N circles, we don't really have a mechanism to change the gain in the open loop transfer function. And so the approach that we're going to use is to use what's called a Nichols chart, which displays the M circles in units of decibels. Okay, so in the M circles with decibels, you'll see there's my magnitude plot here on the y-axis, and then my phase on the x-axis right here. So we have what's called a Nichols chart shown right there. And as an example, what we're going to do is we're going to take this G of S where we have a gain K, and we're going to start with K equals 1. And we have our 3 poles, 0, minus 1, minus 2, that I have right there. And so what we're going to do is we're going to take this transfer characteristic, starting with a gain of K equals 1, and we're going to sweep that from a frequency from 0.1 to 1 radians per second. So if I look on this Nichols chart, I'm going to have a couple of curves. So first I have this K equals 1 curve, which is really shown here in black. Now I have, that's for K equals 1. And so what I'm doing is I'm starting to sweep it. I start up here at this point at omega equals 0.1, and I'm going down to this point here, which is omega 1. So I'm sweeping. Frequency increasing is going downward, and you'll see all those little dots along the line there. I also had plotted this for a gain of 3.16. So again, that's what I'm doing, is I'm starting with this gain of K equals 1, and I'm sweeping that. Now notice, depending on the value of K, I can look at where my magnitude is at a variety of points here. So again, depending on a various frequency here, if I'm at that frequency, I can go over and say, I'm almost at 0 dB, and I'm at this phase. Okay, so this is another way of sort of graphically looking at, as I'm sweeping frequency for a variety of gains, what's going to happen. So here's a higher gain. Notice those curves essentially shift up. And so what is that gain increase? So from 1 to 3.6. that is a 10 dB increase in log. So 20 log base 10 of 3.16 in terms of the gain. Let me say that again. So let me write that down. So in terms of the 20 log of base 10, in terms of the gain in dB, okay, so the gain in dB, okay, if we have a gain of 3.16, okay, so now a gain of 10 would lead to 20 dB of rise, because you'd get a value of 1 times 20 here. So that's essentially the formula that we're going to do to get a gain in dB of 10. So simply what we do is we take that curve of k equals 1 and we shift it up by 10 dB. So we'll see, 10 to 20, that's a 10 dB shift. So that's what's happening with these two curves. So let's get rid of that ink real quick. Okay. Get rid of that ink. And so going from k equals 1 to 6 at, for example, omega equals 0.1, it's this dot to this dot, which again is a 10 dB increase. So that's how one way we could look at changing these curves. And then again, as we sweep these frequency points, again, frequency increasing that way, we can basically see, oh, here's our 0 dB magnitude, how far can we go? And then again, before we hit a certain phase that we don't want, so we could find, phase and gain margin relative to this plot as well. Okay, and this plot, Nichols, we have this in Nichols chart. We have this in MATLAB as well, so you can experiment it with there, and we'll give you some exercises on that as well. Okay, so this will conclude this module. If you have any questions on any of this material, please don't hesitate to reach out. Thank you.